Hello everyone, let us begin our lecture with some problems we need to solve, which mostly comes in various examinations comparative related to mathematics. That in our question number 1, there is a question that find the number of divisors. Find the number of divisors of n. There n, the value of n is given to us. Then we have to find the number of divisors. So in our lecture 1 and 2 you already know that if in a question if they ask us to find the number of divisors, then that is nothing but our tau function, tau value. There is n equals to 23. So we have to find that tau of n. If we find our value of tau of n, then only we will have the number of divisors. So tau of n, there is an if we all know that 23 is nothing but a prime number. So in our remark number 1 we all know that for a prime number the tau function is always 2, and in second part they asked that find out the sum of divisors of n. So what they asked, the sum is nothing but our sigma value. So sigma of 23 will be, what was that? For any prime number the sigma value are always n plus 1, that is 23 plus 1. Easily we can found that the sum of all divisors of 23 are 24, and the number of divisors of 23 are 2. Similarly we can find the in case of 167 is also a prime number. So tau of 167 is nothing but 2, and sigma of 167 equals to 167 plus 1, that is 168. So we have already solved the question number 1. So in our question number 2, which already came in NBHM 2015's question paper, there they asked find the number of divisors of n. Here n is given, that the value of n is 2520, and they asked us to find the number of divisors initially. So we have to find out the number of divisors of 2520. So to find the number of divisors of 2520, we know the prime factorization of 2520, that is nothing but 2 square into 3 square into 5 into 7. That is, we have to now find the number of divisors, that is tau function. Tau of n will be 2 plus 1, that k1 plus 1, k2 plus 1, here k2 is 2, the power k2 plus 1, 1 plus 1 the power of 5, and 1 plus 1 again. So if we multiply all of us, what we get, that 2, actually it is 2 cube. So we have 2 3, then 2 to the power 3, then 3 plus 1, that we have 4 into 3 into 2 into 2, then the answer will be 48. But here is an extra thing which we have to consider, that excluding unity and number itself. So in case of 2520, what will be the unity of 2520? That is 1, and number itself. Then we have to reduce 1 and 2520 from the list of 48 numbers. So we have to subtract two numbers, 1, that is 1, and 2520 from the list of 48 numbers. Then thereafter we will have the answer, which is 46. So what will be our answer? That if we exclude unity and number itself from the divisors of n equals to 250, thereafter we will get the 46. So using the value of tau function, we easily have the value of all of this. So in our next slides we have a theorem. In this theorem we have that if f and g are two multiplicative functions. So what is a multiplicative function? A multiplicative function is an arithmetic function which satisfied f of mn equals to f of n into f of n. So in this theorem we have the statement that if f and g are multiplicative function, and if f of p raised to alpha and g of p raised to alpha for all prime p and alpha belongs to natural number with 0, that is whole numbers, then we have to show that f equals to g. So in this case, initially we took that for alpha equals to 0, f of 1 are always equal to g of 1, and also for the number n must be greater than equals to 1. So if we consider the number n, we have a unique prime factorization of n, which is p1 alpha 1 p2 alpha 2 dot pk alpha 1. This is nothing but our prime factorization of n. So now we write it in the form of f of n equals to this full n. So we already know as the what is multiplicative function, that there is a function f of m, and we can write it in the form of f of m dot f of n. So here we write as f is already a multiplicative function, then we can write it in the form of f of p1 alpha 1 and p of p2 alpha 2 and dot consecutively p of pk alpha k using multiplicative functions property. So here we have pi and pj must be are relatively primes or co-primes equals to 1 and I not equals to j. So here as in if f of p raised to alpha equals to g p raised to alpha, so since both are equal in case of alpha, then we can write it in the form of this as the form of this, that is g of p1 alpha 1 p2 alpha 2 dot pk alpha k g of n. So here since because in our question we have that g is also a multiplicative function, so therefore we can easily say that f of n equals to g of n for every n belongs to natural numbers. Therefore we can write this as the form of f equals to g. This concludes our proof. So in our next slide we have some definitions. We already know what is perfect square. An integer n is called a perfect square if n equals to m square. Suppose an integer 25 is said to be a perfect square if it is right in the form of 5 square, another integer square form. Another way we can say that if we have an integer n that is 25, if we have the square root of that integer n, then the square root value of that number must be an integer which is 5. There is two values plus minus 5, but we will only use 5 because 5 belongs to positive integers. So this is the definition of positive integers. Here are the examples of perfect square, which is 4, 9, 16, 25, 36. All are nothing but our examples of perfect square. Now what are square free numbers? An integer, any integer m greater than n is called an square free integer if for any m belongs to natural number excluding 1, m square not divides by n. So if we take that square free number, if we take the if we take a number 35, if we see that the prime factorization of 35, that is 1 cross 5 cross 7. So if we deeply log into the prime factorization of 35, there is 1, 5 and 7. Is there any number which is a squared number? No, na. That means 35 is a square free number. Anotherly, if we take an example of 12, that is 2 cross 2 into 3. So we can be easily write it in the form of 2 square into 3, that is 2 square is a square number, therefore 12 is not a square free number. So if we have the examples of therefore 35 is a square free number, 21 is a square free number, 7 is a square free number. Anotherly, we can there is a remark, we can easily say all primes are square free, isn't it? So 20 is a square free or not? If we see the prime factorization of 20, there is 2, cross 2 cross 5. So here again we have 2 square, which is a squared number, which is a squared, because there exists an a square in the divisor of the numbers. In another form, we can easily say that if in the say I am writing, if in the list of divisors, if in the list of prime factorizations there exists an a square in the there exists an a square in the list of prime factor, if there exists an a square, we can easily say, to define the term square free, so next if we log into our next slide, there is a question, there is a result. Actually, this is the result of a proven statement that show that an integer n greater than 1 is a square free integer if and only if n is a product of distinct primes. So what is this? Show that an integer n greater than 1, there exists an integer n greater than 1 is a square free. Obviously that will be a square free integer if when the n is a product of distinct primes. What did we know about the term distinct primes? Distinct primes are known as, if we are 2 cross, so what will be that number? 210, I guess. 210. So if we look into the prime factor ratio of 210, there it is consist of 2 cross 3 cross 5 cross 7, all are distinct primes. Distinct primes means all comes in only once. So if we look into our proof, then the n is a square free integer. It is given that that means n must be greater than or equal to 1. Greater than 1, we have the prime factorization of n. We know that from our lecture 1 that we can easily write the n as a product of prime factors p1 alpha 1 p2 alpha 2 pk alpha k. So there is a twist that as that n is consist of distinct primes, that means all ai equals to 1. Ai means the power of p1 p2, that means alpha 1 alpha 2 alpha k is all writing in the form of ai alpha I, where I equals to 1 to dot k. Then that means pi square divides our p square divides, we are taking an example, we are taking an if possible alpha I greater than equals to 2, if possible. That means pi square must be divided by pi alpha I. That means pi square can be written in the form of pi alpha I. Anotherly, we can say that pi alpha I divides n. That means we can easily write this in the form of as pi divides pi square divides pi alpha I. Then we can write also that pi square divides n. Now for any alpha i's, by this thing that pi square divides n, we can easily say, what did this implies? This implies that n is not a square free integer. If n is not a square free integer, which is a combination to the which is the contradiction of our fact that n is a square free integer. If n is a square free integer, then there must not be exist any pi square in the list of prime factors of n. That means we can easily write that alpha, for any alpha is equals to 1, n equals to p1 p2 dot pk. That means this will be the prime factorization of n, because all p1 p2 p dot pk are distinct elements. Therefore we can easily write that n is a product of distinct primes. So in this proof, conversely we can say that n be a product of distinct primes. That means we know that n can be written in as n is the product of the distinct primes. That means n can be written in the form of p1 p2 dot pk. So our new claim is n is a square free integers. As we prove conversely, that means we can say this is our converse statement. Which one? This one is our converse statement. So we can write that n is a square free integers. That means also n is a square, if n is a square free integers, therefore there exists a m greater than 1 such that m square divides n. Also we can write that if m greater than 1, m has prime divisor p. Any integer greater than 1 has at least one prime divisor. We all know have that any integer we can say 3 has at least one prime divisor, because 3 has only at least one that means any numbers which greater than 1 has at least one prime divisor, that must be that number itself or any other number, any other integer, any other prime divisor. That means we can write it in the form of p divides m. We also wrote in the form this, there is a correction that p square divides m square. Again, by transitivity we know that the proof from our first lecture of the divisibility, that if a b c are 3 consecutive, then they must hold the transitivity property. That again by transitivity p square divides n, p square, and we have that n equals to n is written in the product of prime vectors, that p square divides any of the prime vectors of p1 p2 that pk. But we already know that p1 dot p2 dot pk are it is not possible because they all are distinct. So for any p square there not be any p1 square or p2 square dot dot pk square to be satisfy this statement. So our supposition is wrong, whatever we suppose, which is not possible as n is a product of distinct primes. That means n is a square free integer. So this actually this one statement is very important, because this statement is, we can say that this statement is one of the Ramanujan's development. This theory made by the development of Ramanujan's theory, whatever we have in the notebooks of Ramanujan. We all know that this is to know, we have to know that the Ramanujan's work has been published in the form of some notebooks. So in this statement, that in usual notation prove that product of d equals to n raised to tau of n and 2. What did this sign means? This sign means we all know that this sign means summation, and this sum means product of something, product of suppose there is a1 into a2 a3 a4 a5, then we can write this in the form of product of something ai. So in usual notation prove that product of d equals to n raised to tau of n divides t. So we start our statement by we know that d divides n. If and only if there is a, if d divides n, we know that we can say that if d divides n, then n by d must be divided by n. So we can give n by d as we can write n d dash. We can assume that so if tau of n equals to j and d1 d2 dot dj be the j divisors of positive integers of n, because n must be have divisors, that we can assume writing that d1 d2 dot dj are the j divisors of the integer n. Then if we consider the product of dj, what is dj? dj is the number of divisors of the number of the integer n from I to j, and dj dash, what was dj dash? dj dash was our another function, that is I1 product of I equals to 1 to j. So this statement same, we are finding the product of di and product of dj itself. We can know that there is a, we can already assume that d dash can be, we wrote in the form of n by d di. So we can write in the form of n by di. We already have di, so if we include both, the di equals to n by dj, and di cancelled out, and we already only have n. N means the product of j times. Here I equals to 1 to j. That means the if this removes out, then we have only n, because then n runs must be from 1 to j. That means n1, n2, n3, j times n. So we can write in the form of nj. So also the product of if the product of dj equals to dj dash, that means if I wrote in the form of this di square equals to nj, we just from our early example. So what did we have? That if we say, we all know that by the exponent, if exponent goes there, that will be j by 2. Then there is, what is j by 2? J by 2, j by 2 is nothing but our tau of n by 2, which concludes our proof. So in next we have an example that if n is a square free integer, then we have to prove that tau of n equals to 2k, where k equals to number of primes in the prime factorization of n. Because we know that n equals to n by the fundamental theorem of arithmetic, that n has a unique prime factorization of p1, p2, pk of the primes, product of primes. Then n is a square, and it is given that n is a square free in our first statement. It is in our statement it is given that n is a square free integers. So n represents the product of distinct primes. Here it is all the p1 distinct primes. So if we write in the form of tau of n, obviously every number have the power 1. Suppose p1, k1, p2, k2, p3, pk n equals to, if we write in the form of, in normal case, p1, k1, p2, k2, pn, kn. So here, as it is a distinct primes, the ki value is must be equals to 1. So the equal 2 dot 2 dot till k times 2, that means we have the answer of 2k. So in our next statement we have a question which is mostly come in various examinations, which already having the question of Barton's the elementary number theory book. There it is given that verify that tau of n equals to tau of n plus 1 equals to tau of n plus 2 equal to tau of n plus 3, all are equal, holds for the number n equals to 3655 and 4503. So we must need to find the prime factorization of 3655. Here n is 3655 and n plus 1 equals to 3656, n plus 2 equals to 3657, and again another n plus 3 equals to 3658. If we write the prime factorization of these numbers, then 3655 means this will be the product of prime numbers, which is 5 into 17 into 43, and 3656 is the product of 2 cube into 457, which is prime number, and 3657 it is in the written in the form of 2 into 23 into 53, and 3658 which can be written in the form product of 2 into 31 into 59. So if we write the tau of n, here we have tau of n equals to, tau of n means 3655. If we write in the tau of suppose tau of 3655, the value will be 1 plus 1, all are distinct, k1 plus 1, k2 plus 2, and k3 plus 3. The product of k1 plus 1, k2 plus 2, all are 8. And similarly tau of 3656, we have the power 3, k1 plus 1 and k2 plus 1, which is also 8. And if we go for 3657, then we also get 1 plus 1, k1 plus 1, k2 plus 2, and k3 plus 3, which is 8. That means what was our answer? That is 8. And if we go for our 3 6 5 8, we'll have that 1 plus 1, k1 plus 1, k2 plus 1, k3 plus 1 again, because all are distinct here. That is 8. So we can easily show that tau of 3655 equals to tau of 3656 equals to tau of 3657 equals to tau of 3658. That means tau of n equals to tau of n plus 1 equals to tau of n plus 2 equals to tau of n plus 3, which concludes our proof of the statement. So in the second case, we on the second case of n equals to 4503. Let me rub the question. In the second part of the question, n is given to us that the value of n is 4503, that 4504, 4505 and followed by 4506. If we look into the prime factors of 4503, then we'll got the product of 3 cross 19 cross 79, which is nothing but the product of distinct primes. Thereafter we will got 4503. In case of 4504, we will have 2 cube cross 563. Can we say this is a square free number 4504? No, because there exists an m square, that is 2 square exist 563. And in case of 4505, then we can write is 5 product of 5 cross 17 cross 53, which is a square free number because this is the product of distinct primes. In case of n plus 3, that is 4506, we can write in the form of 2 cross 3 cross 751. Then that means tau of 4503 equals to, again we have 8. Then tau of 4504, we have 8. You can find it out by using the tau formula k1 plus 1 dot k2 plus 2, k2 plus 1 dot k2 plus k3 plus 1 formula 4505, that is 8, and followed by 4506, that is also 8. So that means we can easily write in the form of tau of 4503 equals to tau of 4504 equals to tau of 4505 equals to tau of 4506 equals to 8. That means tau of n, in this case also tau of n dot tau of n plus 1 equals to tau of n plus 2 equals to tau of n plus 3 holds, which is equals to 8. So in our next question, in this question they asked that then establish that for